Let's do Quadtrees in half an hour. I want to make a map editor, and Visual Studio has failed me, so we're just going to do it from scratch in half an hour. I don't know. Let's do this. Okay, so we are going to make a quad tree. Do you guys know what a quad tree is? Quad tree is a data structure in which we talked about BVHs before. It's an acceleration structure, right? Let's talk about quad trees. So quad tree is a binary tree with 4 kids, right? Hence the name quad tree. Although typically we oftentimes don't visualize it like this. Instead, we visualize a quad tree spatially. So if you have a 2-dimensional space, then oftentimes you will divide it into 4 quadrants, and each one of those you have the upper left, the upper right, the lower left, and the lower right. And so the root that represents the the entire level essentially has 4 kids: the upper left, the lower left, upper right, and lower right. And then if these pointers are null, that means nothing is in it. If they are not null, that means there's stuff in it. And so you can then further subdivide. I guess I'm using purple for my things, and so we further subdivide into 4, and if they're pointing at null, there's nothing there. But let's say we have a point, what's that, the upper left? Let's say we have a point right here. Then that would be in the lower right chunk of the upper left, and so that would be this one. And the other ones would all be set to null. And then you can just further subdivide and subdivide and subdivide. Or you can just be like, if the count is 1, you're done. Right? There's a lot of different ways you can do quad trees. But basically, these could all just be null pointers. And then this could be just a point, essentially. So either a quad tree contains 4 kids, or it contains none, right? And in this case, 3 of the kids are null pointers, right? And if it contains none, it's a root node, then, or not a root, sorry, a leaf node, then it contains a point. And so you can use this to store points in your quad tree, and the quad tree will divide itself up, kind of like this. And if you put a second point in here, then it'll further subdivide. And if you put a point here, it's fine. Put a point here, it'll further subdivide, and so on and so forth. And so it is a spatial acceleration structure. You can use these things very quickly. For example, if the player is here and shoots a bullet this way, if these things are all null, you know that there is absolutely nothing within this space that the bullet can hit, right? Miss, and then you come to here, you exit here, and then you do a ray rectangle or a ray, well, I guess this is a point. Yeah, you do a ray point test kind of thing. Maybe it's a sphere, whatever. It misses, so it travels onto this one. This is a null one, and it exits the world. We're done. And so it allows you to do fast collision detection. Quad trees are extremely popular in 2D. In 3D, you add another dimension for the depth, right, or z-axis, or whatever you want to call it. And it's an octree. So an octree is a 8-kid tree, and you have 8 subdivisions, right? You divide it in half this way. Let's see if I can draw it a little better. And so you've got the upper left, the upper right, the lower left, the lower right on the top plane, and then on the bottom plane. So you cut it in 3 planes. And there you go. So does that kind of conceptually make sense to you guys? So we're going to just hold a bunch of points, because points don't have space, so we don't have to handle the case where like you have something edging over a boundary and things like that. So we're going to make a point class, point, double x and y values, and just initialize them to 0 just because it makes me happy. And then we are going to make a quad tree class. Quad tree. And every quad tree has either leaf equals true, I guess. And so it defaults, let's see, point P. So either it contains a point or it doesn't. If it doesn't contain a point, then it will have 4 kids. So this will be 4 quad tree pointers. Quad tree pointer upper left, upper right, lower left, lower right, and all of these, of course, will be initialized to null pointer. To 0. I'm not being a good C++ program here. I'm using structs instead of classes, but we've got 20 minutes left in class. So let's do this. Okay. So we got our quad tree. We're going to start off with a quad tree pointer called root, and root is going to be equal to a new quad tree, and okay. I'll be a good programmer, I guess. Quad tree const quad tree reference q equals delete. And we are going to make a quad tree constructor that does absolutely nothing, and a copy constructor that's deleted, and a destructor that will delete the kids. Well, I'll always follow the rule of 3. Okay. Delete ul. Delete upper right. Delete lower left. Delete lower right. So that'll delete the tree for us. At the end of the day, I'm being not a great programmer. I'm not really following good design principles, but we got 19 minutes. So, and then void operator equals taking in a const quad tree by reference q equals delete. Also, I'm following the rule of 3 by deleting the copy constructor and the assignment operator. Okay, so okay, so let's do this. So we need to make a insert function, and we need to have some way of traversing the tree. So rather than doing doubles, let's do ints. That way we don't have to worry about rounding errors and mismatching and stuff like that. So we need to have a insert of some sort in here. We need to have a delete, maybe. Nah, who cares? We need to have a search in here. And probably at some point, like some sort of array cast or something like that, return false. Search, yeah. And so array cast, you'll shoot array, and then it'll tell you if it hits a point or not. No. All right. But we'll worry about that later. Doesn't even have any parameters right now. Okay, so for insert, we are going to be inserting a point into the quad tree. So we're going to make a const point by reference named p. And let's do this. So we need to have, that's the big thing we do need to have is we need to have a size. So we need to have, we need to know what square region, rectangular region we are over, right? So maybe the quad tree by default will be 0 to 100 or something. Then each quarter will be, 50, right? Does that make sense? And then half of that would be 25s, and then you get rounding issues and stuff like that. You guys with me? You guys remember data structures? You got 17 minutes. Ask your questions. So int min x int max x. Let's just do 2 points instead. Yep. Point min. Can't use a default anymore. And we are going to have min and max. If we are a leaf, then this is the point E container. Root's a weird case because it's not a leaf. Let's default as false. Okay, we'll figure it out. So technically, the first time we insert into root, it should just be a leaf. Yeah, how do we want to do this? Technically, you don't need to subdivide until you've got 2 kids. Oh, whatever. Leaf just means we hold a point. Let's put it that way. Okay. What are we using the size for? Which size? This is like the extents of the quadtree, right? So, you know, if you have a rectangle, we would need to know the starting point and the ending point in the row and column, right? This is the region of space we are encompassing. Because it's a spatial algorithm, right? So we need to say this, and we need to say going from 0, 0 up to 100, 100. You're mad at me? What are you mad at me about? Okay. Fair enough. That is a me problem, not a you problem. Okay, and so this points to actually. There we go. So, okay. So we're going to hold a region of space. Now we're going to insert things into this, and then we'll figure that out. So let's do this. So root points to insert. Let's insert. I don't know, 30. And so insert is a const point. Okay, cool. All right. So if we are not a leaf, then it's pretty easy, right? We just become a leaf. Leaf equals true, and our p equals the new p. There. And so that's pretty good. And so this will handle the base case. You insert into an empty tree, and then boom, there's a point in there, and then yeah, all right, cool. Should we figure out a midpoint, a dividing line? That might come up a lot. Yeah, let's maybe cache that. Okay, so min, mid, and max. So we're going to pass in min and max, and I'm actually going to create a new thing called the midpoint, which is the dividing line, because I figure I'm going to be doing this a lot. So let's do it this way: mid x equals min x plus max x quantity divided by 2 by p. Do the same for y. So this is the dividing line rounded down. So 25 divided by 2 is 12. And so 0 to 12 will be on the left, and 13 to 25 will be on the right. And so it's 0 to 100 inclusive. So it's including these points. So that's the dividing line. And okay, so that is that. And then we return. Okay. And going back the other way on search. So search is going to have to take a point as well. And so if I am a leaf, then it's pretty easy. If p equals my p, return true. And let's see if we can generate a comparison operator. Nope, can't do a comparison operator for free. So let's say auto operator that equal const point p equals and it made, no, did it? I don't know. Let's find out. This is C++ 20 magic. Must be const. Yes, thank you, thank you, thank you, thank you. Did you guys see that? Did you guys see that? Did you guys see that? C++ 20. Pretty cool stuff. So this thing here is called the spatial operator. One of the benefits of you being an IS-50B is that you get to see advanced cool stuff being used. This actually generates all 6 of the comparison operators, not equal to, less than or equal to, greater than or equal to, all of them for you automatically, and it just uses whatever member variables you have, and it just does them in lexicographic ordering. So it'll use the x values first, and then the y values second for less than and things like that. We're not using less than because it doesn't make any sense, but it will certainly generate a comparison operator for you that just checks to see if the 2 x's are the same, the 2 y's are the same. Cool, good to go, we're done. I don't have to write an equals operator and a non-equals operator and all the other stuff. It is just automagical BS thanks to C++ 20. It's cool stuff. It's called the spatial operator because it looks like a TIE fighter, but they didn't want to get into copyright conflicts with Disney. Yeah, that's cool stuff right there. Okay, so we got this. Okay, so cout root.search for 3030. Let's just see if this works, and let's do a little bool alpha here. And there we go. It's in the thing, and let's do it again for 2030. And it's not in the thing. Cool. Everything's working so far. Now we need to make it a quad tree. We've got 10 minutes left. Let's do this. So that and that is all covered. So now we need to do the subdivision. So if we are a leaf and we're putting a second value in, we need to chop our tree. And oh, actually, we need to check to see if it's a duplicate first, right? So if we are a leaf, which is here, copy paste, there we go. If it's a duplicate, return, discard duplicates. Okay, easy. Okay, so once we get past this point, there's now a second discrete point somewhere within the quad tree. So it is like, you put a thing in here, then it has to divide it up. Okay, and it can keep subdividing, in fact. So, we need to make four kids. Our kids are all null. They should be. I don't think they could ever not be null up until this point. Okay. So first of all, we are no longer going to become a leaf, right? Because now we're going to be an intermediate node, and we're going to have to insert both our current point and the new point into our 4 kids. Yay, good times. So, we're going to make 4 kids. So, upper left is equal to new quad tree, and it's going to take, the upper left is going to go from the minimum point to the midpoint. See why I did that? See why I computed it? And the upper right is going to go from the I need to sketch this out. So we have here, I'm going to draw it not in screen coordinates, but in normal Cartesian coordinates. So let's say we've got our thing here, we've got a point already in here, and we're going to be inserting something. The midpoint is here at 50-50, so that's actually the bottom left, sorry. That is going to be the lower left. Here. And then the upper right is going to go from the midpoint, this is the midpoint, to the max. So that is going to be the upper right is going to go from mid to max. And then for this one, it's going to go from min.x and mid.y, min-x and mid-y, over to mid-x and max z. I apologize for the handwriting. I could do it better, but we're running out of time. Yeah, I'll do it anyway. Okay. So mid-x. Do you see this? This is mid here. So mid-x is this way. Mid-x. Min-x, mid-x, max-x. Right. So it's going to go from mid-x to maximum, not z, to maximum y. There. And that's going to be this quadrant here. That's the upper left. That's Okay, so the upper left is a new quadrimetry going from 2 points in there. I'll do that for upper left, lower left. Do that in a second. So upper left is going to go from, what did I say, min x to mid y. And the other one is mid x to max y. And then for the lower right, the x value is mid x here, and it is min y for the y coordinate. And this spot here is max x and mid y. Okay. Does this make any sense to you, or am I just like babbling at this point? Mid x. No, yeah, min y, and then max x, mid y. Okay. Yeah, see that? I'm breaking a rectangle into 4 subrectangles. So by making that midpoint there, it just makes all the math easy. I don't have to have a lot of divisions by 2 and stuff like that. You see that? So you just kind of have to like look at the things and give them a name, and then you punch them all in, and we'll find out later if it works. So we've got our 4 kids now, and now we just need to recursive. We need to figure out which kid the point's going to. And there's 2 points that are going to be inserted, right? Your current one and the new one are both going to get inserted. And so let's see if there's a way of doing this easily. Let's make a boolean inside, taking in a const point ampersand p. And so we're going to see if a point is inside of a rectangle. Okay. So we've all done this before, right? So if p.x is greater than or equal to, if min.x is less than or equal to p.x, and p.x is less than or equal to max.x, and min.y is less than or equal to p.y, and p.y is less than or equal to max.y, return true, else return false, just return that. Okay, so now we've got a function. You pass it a point and tells you if it's in its range. Cool. So if cling D is crash, cool. If ul points to inside, passing in. Okay. Oh, right. We only do this if these are null. Okay. If ul is null, we're going to make 4 kids. Okay. Because, you know, after you've made the kids, more points will come in and just pass them through, right? Okay. If p is inside of ul, then ul gets recursively called down to insert p. yy 3p, lower left, upper right, lower right, lower left, upper right, lower right. And that will do the recursive call on the point we're inserting. The only other thing we need to do is our current point is getting removed. And so we need to pass that down as well. And so this points to p. So we had a p, right? So we had a point that we're holding. And once you get a second point, then you not only have to pass the new point recursively down to the kids, but your current point gets knocked out, and that has to get passed down as well. So, but you only do that when you create the kids. Then you recursively pass it down to the whichever kid it matches. And then either way, you will recursively insert the thing. So let's see if this works. We need a recursive search too, but yeah, in fact, we do need to do... Oh, no, we're out of time. No. Okay. If leaf. Okay, if we're not a leaf, then we're past this point. And so all we need to do is... if we're leaf, return true. Else, return false. There is search. And then if we're not a leaf, then we just recursively call down. I have 1 minute left. Let's do this. If inside, rather than we will do a return. Vim powers activate, not insert, not insert. We want 6s search. And there we go. We're done. And we'll just do a return false just to shut up the warning. And there we go. So everything works fine. Now let's find out if it works with the recursion. That was Quadtrees in half an hour. So there you go. Yeah, not too bad. Not too bad for half an hour's worth of work. Let's find out if it works or if it seg faults horribly. I'm confident it works fine. Let's just stop the video here. No, I'm kidding. All right. So let's insert it twice. Test that. That's fine. It's good. It discards the duplicate just fine. All right. So let's insert 30, 30, and let's insert 60, 60. Now we're going to go recursive. Let's find out. Okay, it works. Hey, true, false, true. RYP, let's do 61. True, false, true, false. So far, so good. All right, let's insert 31, 31. This is going to trigger a bunch of recursive calls as it divides down to get small enough to have a line between the two of them. Could be an off by one error. I haven't checked. I haven't done the math. Who knows? Let's find out if it works. 31, 31. Infinite loop. Yeah, that's what I thought. I haven't checked for the boundary conditions on that. So can't say you got all you'll watch the real lecture. It seems like it's pretty useful. Yeah. This is what I want you to do for your next assignment. Okay. So let's see. Find out what. Pretty sure I know what the problem is, but let's just do this real fast. And gdb a dot out and run it. Run. And it died in a malloc. Oh, interesting. Backtrace. Yeah, infinite loop. Look at that. So, yeah. Mm-hmm. Yep. Yeah, rounding errors, sure. No, actually, print. Where am I? Print. Let's see. C outs for the win. Let's do this. So, teach C++ how to see out a point. Okay. And prepare for infinite loop. There we go. So min and see that, yeah, min and mid and max are It's yeah. Do you see what the problem is? They're shaved down to size 1, and it can't shave down any further. So it's infinitely recursive. Let's do this again, piping it through head. So it starts off from 0 to 100. It then goes into 0, 25, 50, and then it goes 25, 37, 50, and then divides there, then it divides there, then it divides there, size 1, and essentially size 0 at that point, right? But size 1, and it can't subdivide any further. So, no. Maybe that'll be a fun exercise for you to debug. Do you see what the problem is? Stover, Grante? Yeah. And so if we were to move the numbers a little bit further apart, that's why it's always important to test your code. Works like, oh, actually that one's segmented too. Huh. It's probably in the... It's crash inside of inside. Oh. It's calling inside on an old pointer. Yeah, okay. Right, so if it's a leaf, so how can it not be a leaf? If it's a leaf, if it's not a leaf, its kids should be... Oh, I see. It's because it's not defaulting to true. Yeah, right. Yeah. Okay. So root's going to be a little weird because it is not a leaf to begin with, I think. It becomes a leaf when you insert into it, then it turns into not a leaf again. Right? Yeah. So it's not a leaf. Ah, shoot. Yeah, okay. And so all of these guys should be set to... You know what, there's probably an easier way of doing this. And that is simply to... So if they're null, it doesn't recurse further into them. Works fine, except for there's that rounding problem, right? When you try dividing things over and over again, you end up in a circumstance where you can't divide them any further because they're like 0 apart, you know? And so you can't further, so it turns into an infinite loop. Yeah, I'll just leave this as an exercise for the reader to solve. It's not hard to solve, but it is sort of annoying. Oh, I already have a quad tree. Let's make a new directory called Quadtree2. I'm going to move the main.cc into here, and your thing is to part 1 your homework is going to be to basically make a map editor. That's what I wanted to do in the SDL earlier, but Visual Studio either sucks or I'm too dumb to figure out how to make it work. One or the other, maybe both. I don't know. So what I want you to do is make a map editor. Okay, so step 1, fix the infinite loop that takes place if you put 2 points next to each other in the quadtree. That's actually good exercise for you. It's the kind of bug that comes up all the time. So your code's correct, right? Except when you get down to it, it's not. And step 2, make a map editor using the colors library. The keys, colors, and relib libraries. The user should hit the keys 1 through 8 to pick different colors, and then you click on the screen and color the pixel at that location, that color. Hold each click into the quadtree. Write it to disk. Can just be a text file holding the numbers 1 to 8 for the colored pixels and 0 for any unclicked pixel. Traverse the quad tree to do this. Or I don't know. That might be a little bit wasteful. Do this. Format. X, Y, color. Okay, so don't write any uncolored pixels to disk, just the places they clicked. A new click will overwrite old click. And so this is like a very simple MS Paint implementation, right? You can color, it's like a sprite editor. You can color, make images, okay? So the format is the X, Y, actually, yeah, sure, whatever. Yeah. Example, 10, 20, color 4, 11, 3, color 8, 40, 20, color 2, etc. Okay, you guys understand? So you've got a kind of working quadtree, like all the recursive stuff, like the stuff that breaks your brain, it's done for you, right? Vim main.cc, don't need UAU technically yet. So, yeah, raycasting, yeah, whatever. Okay. Get rid of that. Debugging. You probably want to put it back in. But... all right. You guys cool? You do that? And I'll have you know that we're actually going to need you to actually do this by next Tuesday, because this is going to be the map editor used in the last assembly class assignment. You're going to make a map editor, and students are going to use it to Dijkstra's across a map. So each of the colors is going to represent a different cost, and you know, so you could have roads and rivers and things like that. And so you're going to navigate with different tiles on the map, having different costs to it. Okay. Wait, I'm going to use this? Yeah, you're actually going to have to use this in 45. In fact, everybody in 45 is going to use your code. Okay. Maybe color 8 is gray, and that represents a wall that's impassable. Maybe color 4 is blue, and that's impassable. and then green is grass, and brown is a road, and things like that. So think about which colors you're going to put in there. 0 would erase a point. Anything that's 0 is out of the world, doesn't count. So you're going to make a Zelda-like map editor kind of thing. Okay. Time for some job security. Yeah, you'll have a competitive advantage in 45 having made the map editor, right? Okay. Stover, you good? All right. So hope you learned a little bit. This is a Quadtrees and Octrees, the 3D version. Very useful. They come up all the time. The Bridges people just did a Quadtree implementation, and they had it up on their poster at SIGSI. So it's I used it in my master's thesis. It's used all the time. Mr. Bell, who you see drop in here from time to time, he used Quadtrees to do his collision detection kinds of things. Yeah, so when something moves, it drills down to the Quadtree to see if there's something there. If there's not, no collision. If there is, do a rectangle, rectangle, okay, collision, that kind of thing. Super useful stuff. And you got a pretty good starting point, so should be good. All right, peace out, you guys. I'll see you next Tuesday.